Okay guys, to round out our study of acids and bases, we're going to look at what's actually in chapter 21, not in chapter 20, but we're going to be looking at neutralization reactions, how acids and bases neutralize each other, and how we can do some stoichiometry with those balanced equations. So here's what's happening in an acid-base reaction. When an acid reacts with a base, water and salt are produced. Okay, this is going to be a double replacement reaction like any other that you've seen. We're just not making a precipitate, we're making water. Now when we use the term salt, we mean any compound that contains an anion from an acid and a cation from a base. And when we get our final product, because it's water and salt, there are no acidic or basic properties, so we have neutralized the acid and the base. So in our examples, you can see that we have HCl, which is an acid, reacting with NaOH, which is a base. The H and the Na are the cations, so they're the ones replacing each other. So the H goes with the OH to make water, and the Na bonds with the Cl to make the salt, which is sodium chloride. Now this one is in a 1-to-1 mole ratio. When we look at H2SO4, which is sulfuric acid, reacting with KOH, because there are two hydrogens, we're going to need two hydroxides to make two waters. So it's actually going to be a 1-to-2 mole ratio with the acid and the base. All right, so let's try one on our own. So we have HBr, hydrobromic acid, reacting with potassium hydroxide. So the H and the K are going to replace each other, which means we're going to make KBr plus 1 minus 1. So our salt will be KBr, and then the H and the OH make water. So it is making the salt and the water, which is neutral. Now, to figure this out in a lab, we do what's called a titration. Okay, and a titration is just the name of the lab technique that you're going to use to figure out the amounts of things that need to neutralize each other. So we're going to get the balanced equation, or we're going to use the balanced equation to get the mole ratio. There's an N there that shouldn't be there. Ignore that N. The concentration of the acid or the base can be determined by performing a neutralization reaction. And we're going to use an acid-base indicator to show when neutralization has occurred. Now usually this is an indicator called phenolphthalein. As you can see in the picture, phenolphthalein is colorless, and when you get to that neutralization point it turns pink, so then you know that the solution has been neutralized. So that's what we're going to be using when we actually do the titration. Okay, so here's how it works. First you're going to have an acid that you don't know the molarity of, and that's what we're trying to find. What's the molarity? And so we're going to measure a specific volume of that acid and put it in an Erlenmeyer flask. And we're going to put several drops of indicator into the acid. So down here, this is what we would be starting with, an Erlenmeyer flask. The indicator is colorless when it's acidic, so this is what we're going to start out with. And then we're going to add base that we know the concentration of until the indicator just barely changes color. Now, to do that, we're going to use what's called a burette. And this is a burette right here, okay? Now, the burette dispenses liquid out of the bottom of it. So we're actually measuring how much comes out of the burette and goes into the flask. And you can see the bottom of the burette right here. So what we're looking for is just a barely pink solution. That's when we want to stop. If you get really bright pink, you've gone way past the point of neutralization. So our goal is to get that really light pink color. Now, there are 3 vocabulary words you need to know. A standard solution is a solution of known concentration, and that's what we add using the burette. When we do this lab, that's going to be the base. You're going to know the concentration of the base, and you're going to have it in your burette to add to the acid. And then we have 2 points. The end point is when the color changes, okay, and that's when you stop adding base, is when you get that color change. And ideally, we want it close to the equivalence point. And the equivalence point is the point at which equal numbers of acid and base have reacted. The equivalence point is the point of neutralization, where we've completely neutralized them, we don't have excess of either one, and it's a neutral solution. Okay, so we hope that color changes around the same point at which we have a neutral solution. Okay, so let's do the math examples of what would happen here. We want to know how many milliliters of 0.45 molar HCl must be added to 25 milliliters of 1 molar KOH to make a neutral solution. Well, because we're doing stoichiometry, what's the first thing we need? A balanced equation. So we're going to write out our balanced equation. We're going to have HCl plus KOH. Figure out the products. The H and the K replace each other, so we'll get KCl and water. So because we have one of each, H and OH, this is a 1-to-1 mole ratio. Okay, now when you're doing the stoichiometry, you always want to start with what you know the molarity of. Here, we know the molarity of the KOH. So we're going to start with 25.0 milliliters of KOH over 1. Okay, we want to convert that to liters. Now, here's a new part. Think about molarity. We know that molarity is moles per liter. That means we actually have a conversion factor that we can use in our stoichiometry. So 1.00 molar KOH means there are 1.00 moles of KOH per liter of solution. So we have a new conversion factor. 1.00 moles of KOH per liter. So now our milliliters have canceled, liters canceled, and we have moles of KOH. This is where we go to the mole ratio. And we said from our balanced equation, 1 mole of HCl is equal to 1 mole of KOH. Okay, mole ratio from the balanced equation. So we cancel those. Now, there are two things you could do here. It depends on what you're trying to find. If you're trying to find the molarity, you stop with moles. If you're trying to find the milliliters, we use the molarity to get there. So here, 0.45 moles per liter of HCl. Okay, so we want our moles on the bottom. So 1 liter of HCl is equal to 0.45 moles. So those cancel. And now the question asks for milliliters, so again we convert back to milliliters. So when we do our stoichiometry, we get a grand total of 55.6 milliliters of HCl. Okay, so there's our stoichiometry related to acids and bases. Okay, let's do another one. What is the molarity of NaOH, a sodium hydroxide solution, if 48.0 milliliters are needed to neutralize 35 milliliters of 0.144 molar sulfuric acid? So, balanced equation, sodium hydroxide plus sulfuric acid. Okay, now we have 2 H's, that means we need 2 OH's to make 2 waters. And then sodium, which has a charge of +1, will go with sulfate that has a charge of -2 and give us Na2SO4. So now we have a 2-to-1 mole ratio. Okay, let's look at our question. What is the molarity of sodium hydroxide solution if 48 milliliters is needed to neutralize 35 milliliters of 0.144 molar sulfuric acid? We know the molarity of sulfuric acid, so that's what we start with. We start with 35 milliliters of our sulfuric acid, H2SO4, over 1. And then we're going to convert to liters, so that we can use our molarity here as our conversion factor. So in 1 liter of solution, we have 0.144 moles of H2SO4. Now we need our mole ratio, 2 moles of NaOH for every 1 mole of H2SO4. Okay. Because we're trying to find molarity, we want to stop here and get moles. So when we do this, that's going to give us 0.0101 moles of NaOH. Now the question wants us to find the molarity of NaOH, and we know molarity is moles per liter. And if we look up here, that's how much NaOH we used. So we convert that to liters, and when we divide, we get 0.210 molar NaOH. Okay. Now, let's look at the actual glassware that you're going to be using. Okay, when you're using a burette, the burette is made to dispense liquid, not contain it, which means we're going to measure how much is coming out, not how much we put in it. So 0 is at the top of the burette, not at the bottom of the burette. Okay. This is a graduated cylinder. Ignore that picture. Let's look at our burette over here. Okay, so you can see the numbers are actually getting bigger as you go down rather than going up. So our volume here at the bottom of the meniscus, okay, we know it's 39 milliliters, 39.1, 39.2. So it's 39.2 something milliliters. So we estimate between the 0.2 and the 0.3. I think it looks like maybe 4. So that means 39.24 milliliters. So for the burette, you want 2 decimal places. Okay, ignore this one. All right, now, one last thing. It's called a titration curve. And basically, if you were to do the titration with a pH meter instead of an indicator, so as the titration progresses, you're measuring the pH every time you add milliliters of your base. If you were to plot all of those data points, you would get a titration curve, and it looks like this. It has this S shape. So on our y-axis, we plot pH. On our x-axis, we plot the milliliters of the base that we've added. And we're going to get this S shape. Okay. Now, that point right there in the middle, that's the equivalence point. That shows us where our solution is neutral, and that's where our solution should be changing color as well. Now, if you look over here, okay, we're going to be using phenolphthalein, and it shows that phenolphthalein actually changes color between 8 and 10, okay, is where it turns pink. But you'll notice this line is so steep, there is very little difference in volume between the equivalence point and where that solution changes color. So it's actually acceptable to use phenolphthalein even though it doesn't change color directly at a pH of 7, which is where we would have a neutral solution. So when you're looking at a titration curve, okay, that middle right here, the middle of our vertical part of the graph, that's going to be your equivalence point. And the milliliters it took to get to the equivalence point, that's what we would use in our calculation. Okay, so if we were to do a titration curve, that's the point, is to figure out how many milliliters of the base did it take to get to neutral. Now, we're just going to be using the indicator. We're not going to be using the pH meters this time, but you still do need to know what a titration curve should look like.